So we are discussing CBSE current electricity standard 12 previous year's questions answers. Okay. Now let us resume this discussion. State the principal working of a meter bridge. In a meter bridge, balance point is found at a distance L1 with resistance R and S as shown in the figure. Okay. So meter bridge is actually just like potentiometer. It has only 1 meter length wire. Okay. So this is the length of the wire of meter bridge, and it is meter bridge is like a Wheatstone bridge. Okay. So suppose balance point is found here. So this length serves as the third arm of Wheatstone bridge. This length serves as the fourth arm of Wheatstone bridge. Okay. And this ratio arms means first and second arm. This two, this is R, and this arm is S. Okay. So for Wheatstone bridge we need 4 resistances. P by Q is equal to R by S. So this meter bridge, half of the portion, half or wherever the balance point is found, left hand portion serves as the third arm. And for null deflection, suppose this is the galvanometer connected. So for null deflection, what we have, if resistance in the first term by resistance in the second term equal to resistance in the third by resistance of P by Q is R by S. Okay. Then galvanometer shows null deflection. Correct. So here in the first term we have R, in the second term we have S, first, second, third we have this balance length L1 into whatever I rho L1. I is the current flowing in this, rho is the resistance per unit length, and L1 is the length. So resistance of up to this point A to J is how much? I rho L1, and resistance of this, the remaining part, total is 100 centimeter. Correct. So this length is 100 minus L1. So it is I, current in the meter bridge, resistance per unit length into 100 minus L1. Correct. So this is the principle of meter bridge. So suppose unknown resistance to be found, if you keep unknown resistance here at any arm, say first arm or second arm, so here you have put the unknown resistance X, and then you change this jockey point at different points. Okay. Wherever balance length is found, means galvanometer shows no deflection, that is the point. We calculate L, and then automatically X can be found. Correct. So let us see, when unknown resistance X is connected in parallel with the resistance S. Okay. Now here this unknown resistance X is connected in parallel with S. S is already there and unknown resistance X is connected. Correct. So balance point shifts to a distance L2. Find the expression for X. Okay. So we have this relationship for meter bridge. P by Q is L by 100 minus L1. This we have already derived. When resistance R and S are connected, so then what will happen? X and S are connected in parallel. Correct. So in parallel, when resistors are connected in parallel, then what is equivalent resistance of this third term? XS by X plus X. Correct. Okay. Let us see this. So my resistance S1 here, this resistance is changed to Sx by S plus X. Now the balance point is also shifted. Earlier when there was no resistance X parallel to S, then the balance length was L1. Now the balance length is L2. Okay. So in place of S we will put S1. S1 means Sx by S plus X. So now we have another equation. Okay. Here now we have two equations, equation number 1 and equation number 2. Correct. So using these two equations, this is simply arithmetic calculation actually, where you have two unknown and you have to find out the value of X. So by calculating these two, we find the value of X here. Next. 1. Series to parallel combination of two resistors is connected one by one across a cell in which case will the terminal potential difference across the cell will have higher value. Okay, so terminal potential difference means EMF minus current into internal resistance. So terminal potential difference is higher in parallel combination as compared to the series combination, because what is happen, where current is higher then terminal potential will be less. So if two resistances are connected, if two resistors are connected in series, then what is the equivalent resistance in series is R1 plus R2, correct? And when two means direct sum of this, and when they are connected in parallel, two resistors are connected in parallel, then it is R1 R2 by R1 plus R2. Okay, suppose then in which case current will be maximum, when the resistance is less then current will be maximum, correct? So in parallel the terminal potential difference is higher in parallel combination. So what will happen in parallel combination, the resistance offered is will be more. If the resistance offered will be more, then what will happen, the current will be less and potential difference will be more. The physical quantity associated with the electrical conductivity has SI unit ohm meter. Identify the physical quantity, ohm meter. So what is this? Resistance is proportional to length, resistance is inversely proportional to area. So wherever we get this type of relations, the resistance is equal to some constant into L by A, correct? The resistance is ohm, rho, L is meter, area is meter square. So ohm into meter is equal to this. So this particular term is called specific resistance or resistivity. Okay, so it is a specific resistance rho. State the working principle of potentiometer with the help of circuit diagram. We have done it many times. So there is a very repetitive question comes again and again. Two cells E1, E2 and internal resistances are R1, R2 are connected in parallel with each other. Obtain expressions for equivalent EMF and equivalent internal resistance of in parallel combination. So this is 5 marks question. Let us see. This is how the circuit is. We know that potentiometer circuit construction, everything is explained here. So you can take a screenshot of it. This is a repeat question. Okay. Now parallel combination of cell E1, E2 are connected in parallel. Okay, so what is in parallel combination, what is same? Potential difference is same. So you calculate I1 here, okay, I2 here. So this is calculation by which you have to find out, and then we have taken the direction of current in such a way that this I1, I2 are the currents leaving the positive electrodes of the cell. Okay, so this I1 comes here, I2 comes here, I goes there. Okay, so I1 plus I2 is equal to I. This is by Kirchhoff's first law, and so VB1 is equal to VB2 because potential difference at this is equal to VB2 at the potential at this. So we have the at this point VB1 minus VB2 is the potential difference across the terminal, which is E1 minus I1 R1. So we can find out I1 here. Similarly, in the second cell we have VB1 minus VB2, E2 minus I2 R2. This is the potential drop, correct? So we can calculate putting the value of I1, I2 here. I is equal to I1 plus I2 here. From in equation 1 we get the value of I here. Okay. So we know that potential difference is equal to equivalent EMF minus the IR. Okay, so put all these values, we will get the value of EMF. Define electromotive force of a cell. See, electromotive force, this term force is misleading. It is not a force actually, it is work. Okay. So electromotive force is the potential difference between the terminal of the cell when no current flows in the circuit. The maximum potential difference between the positive and negative plate when there is no current in the circuit. Okay. Because when the current in the circuit comes, then the internal resistance of the cell comes, and there is another energy consumed here, that is I into R. So then effective EMF decreases by IR. Okay. So if I is equal to 0, no current flows in the circuit, then V equal to E. So the electromotive force, the difference between the two poles of cell, the potential difference between the two poles of the cell when no current drawn from it is the electromotive force. Now a cylindrical metallic wire is stretched to increase its length by 5%. Calculate the percentage change in its resistance. So initial L is the original length. Now change in length is equal to 5% of L is increased, so it is 1.05. Now area also changes, because if you increase the length, then it will be thinner. So area total, but metallic volume will remain some. Initial metallic volume is how much? Area into the length cylindrical, and when it is changed length is how much? L dash. Then area also thinner, A dash. So volume is same. We can calculate the value of A by A dash is L dash by L. Okay, and but L dash by L is our 1.05 that we have already calculated, correct? L dash by L is equal to 1.05. So now therefore R dash by R dash, how area and R dash is related? Okay, so resistance is proportional to the length, and inversely proportional to resistance is proportional to length, and resistance is inversely proportional to the area. So by this way we get R dash equal to L dash proportional to L dash by A dash. R dash is rho, specific resistance per unit length, into L dash by A dash, and R equal to rho L by A. So if we divide R dash by R, we get L dash A by L A dash 1.10. So this is the 1.1025. This is the percentage. Therefore the percentage increase in resistance is R dash minus R by R into 100. 10.25% will be the increase in with the change length. States Kirchhoff's law, current distribution in electrical network. Using this rule, determine the value of current in I1. Okay. So we have already discussed. Repeat question. The value of current I1 to be found here. This current. Okay. So you have explained Kirchhoff's first law and second law. Then I1 plus I2 is I3. So if you draw the circuit here, this I1 current flows here, I2 current goes here, correct? And this I2 current is coming out. In this branch we have I3, correct? So I3 is actually, this is I3. I3 is divided into two parts, two outgoing current. Here at this F point, I3 is in, okay, coming in at this point F. I1 and I2 is coming out. So as per Kirchhoff's first law, I3 is equal to I1 plus I2. Correct. And now applying the loop. So here in this circuit, now let us analyze this circuit. In this circuit, this EMF is connected. In this circuit, EMF is connected, means driving current in the positive direction, current in this direction. So I1 into 20 plus I3 into 40, I3 is also in the clockwise direction, equal to how much? is equal to total sum of EMF. So only one source of EMF is there in this circuit, which is equal to 40. In this circuit we have I2 is the current in this circuit. I2 is the current, okay, and this circuit EMF is anti-clockwise direction -80. So what will happen for this circuit? If we take the below circuit, means now we will apply Kirchhoff's second rule to this circuit, okay. Now when we consider this circuit, this current I3 is anti-clockwise. I3 is clockwise for the A, B, C, F, this loop, but this same I3 is anti-clockwise for E, F, C, D, correct. So if I apply the Kirchhoff's second rule for this circuit, then it will be minus I3 into 40 current into resistance. This is driving in the opposite direction. Positive terminal is connected in anti-clockwise direction, so is equal to minus 40, correct. This current I2, okay, is flowing in the anti-clockwise direction. It will be minus I2 into what is the resistance? 20. This cell is 40 in this cell 40 is in the clockwise direction, correct. So 40 will be plus. This cell 80 is in the anti-clockwise direction, so it will be minus 80. So now we have this relationship. One relation is this I3 is I1 plus I2, correct. And in this is equation 1, this is equation 2, this is equation 3. There are three equations, three unknown, I1, I2, I3. We can calculate it, correct. So you have find out the value of I1. You can similarly find out other values also as required. Now write the mathematical relation of resistivity of a material in terms of relaxation time, number, density, mass and charge carriers. Explain using relation why the resistivity of metal increases and that of semiconductor decreases with the rise in temperature, okay. See, we know that in metallic conduction, as the temperature increases, what happens? The collision, the thermal speed of electrons increases, so the collision rate increases, okay. So Ohm's law is followed in metallic conduction, whereby if the voltage is proportional, the current is proportional to the voltage, okay, and V equal to IR, and this particular resistance increases as the temperature increases. But in case of semiconductor, the relaxation time, that is tau, does not change with temperature, okay. So in semiconductor, the reason for flowing is the holes and the, okay, the charge carriers are depending on what type of semiconductor you have, P type or N type. So it depends about the charge carrier nature, type of semiconductor. So in any case, but the number density of free electrons increases exponentially with the temperature, okay, in semiconductor. So as a result, the resistivity of semiconductor decreases exponentially with the increase in temperature, okay. So this is Child-Langmuir law is followed in semiconductor and not Ohm's law, correct. Ohm's law is followed in metallic conduction. Sketch a graph showing variation of resistivity of carbon with temperature, okay. So if temperature increases, then resistivity decreases, okay. Now two cells 1.5, 2.0 having internal resistances 0.2, 0.3 respectively are connected in parallel, okay. So equivalent resistance is this and equivalent EMF is equal to E1 R2 plus E2 R1 by R1 plus R2. So this is simple calculation. Write the mathematical relation between mobility due to velocity of charge carriers in conductor. Name of the mobile charge carrier responsible for the conduction of electric current I in an electrolyte and ionized gas, okay. So mobility is Vd by E, and the charge carriers in electrolyte are positive and negative ions, okay. So because in electrolyte we have cathode, we have anode, okay. Cathode is the negative, connected with the negative terminal, anode is the positive terminal. So negative ions goes towards the positive plate, positive ions goes towards the negative plate, correct? So charge carriers in electrolyte are positive negative ions, and charge carriers in an ionized gas are electrons and positively charged ions, correct? Now two cells E1 E2, this question E1 E2 in a given circuit diagram, an EMF 5 volt 9 volt and internal resistance 0.3 1.2, calculate the value of the current flowing through the resistance 3 ohm. Okay, so let us find out, because this cell is driving in the positive direction, this cell is driving in anti-clockwise in clockwise direction, this is clockwise direction, this cell is driving in the these two are just opposite. Okay, so this is anti-clockwise direction, so effective EMF because of these two cell will be whichever is higher, that will predominate. Okay, so say E2 is more, so 9 minus 5 is the 4 volt is the effective resistance. Okay, very simple. Total resistance is equal to how much? So these two are parallel, 6 into 3 by 6 plus 3, and these two are series then. Okay, so it is, okay, so 6 into 3 by 6 plus 3, 18 by 9 means 2 ohm. This 2 ohm resistance is connected with the 4 ohm resistance in series, so effective resistance is 4.5. Now 4.5 plus 2 is 6.5. So total resistance is, we have internal resistance also 0.3 and 1.2 is also there. So 4.5 is this. Okay, and this is 2, and internal resistances are also there for these cells. So total resistance is 8 ohm. So effective voltage is 4, correct? 4 is the effective voltage and 8 is the total resistance, so 0.5 is the current. Okay, now this current is your how much? 0.5 ampere, 0.5 ampere. Now this current is split into 2. So so you have to find out current through this, correct? So current through the resistance 3 ohm is how much? How to calculate this? This 0.5, 0.5 splitting here into I1 and I2, correct, is equal to I1 plus I2. Now this I1, 6, now potential difference across 6 ohm and potential difference across 3 ohm are same. So what is the potential difference across 6 ohm? 6 into I1 equal to, what is potential difference across 3 ohm? 3 into I2, correct? And we know that what we have to find out, I2 now. So let us put I1 is equal to 3 2's, I1 is equal to I2 by 2. Now put the value of I2 here, correct? So 0.5 equal to I1 plus I2 is I1 is I2 by 2. Alright, let's do it. You have to do it. Okay. So 0.5 equal to I1. I1 is I2 by 2 plus I2. So it is 3 I2 by 2. 0.5 is equal to 3 I2 by 2. So 2 into 5 means 1. 1 by 3 is equal to I2. Correct. Now 10 meter long uniform cross section and 20 ohm resistances is used in a potentiometer. Okay. The wire is connected in series with a battery 5 volt along the external resistance 480 ohm. If an unknown EMF is balanced at 0.6 meter length of the wire, calculate the potential gradients, means potential per distance of the potentiometer wire. Gradient means this by distance is gradient. Temperature gradients means temperature by distance, correct? So the value of unknown EMF. Okay. So this is the current. Current is equal to total applied resistance. Okay, potential difference across AB. Then we calculate the potential difference, and potential gradient is potential by distance. 10 meter long is the length. This is the way. So unknown resistance is equal to K into the resistivity into balance line I rho L1. So this is the value of unknown resistance. Now power factor of AC circuit, this comes actually in AC circuit. What will be the phase difference between the voltage and current in this circuit? So power factor is cos phi. Cos phi is equal to given as, so in DC circuit we have power is equal to current into voltage, but in AC circuit we have current into voltage into the phase difference between current and voltage. So here the cos phi, this particular term is called cos phi. What is phi? Phi is the phase difference between the AC current and the AC voltage, correct? So it is given directly cos phi is 0.5 means 1 by 2, correct? 1 by 2 means cos 60 degrees, so phase difference is 60 degrees. Draw VI graph for ohmic and non-ohmic materials. Give one example for each. Okay. Ohmic material means what? As you increase the voltage, the current will also increase. But in non-ohmic material, it is either curve or straight line, not passing through the origin, correct? So when V is 0, then current is 0. But in non-ohmic resistance, this current and voltage will not passing through the origin. Okay. The galvanometer will coil of resistance 120 ohm shows full scale deflection with a current of 0.25 milliampere. Okay. So the galvanometer resistance is, suppose G is the galvanometer, its resistance is 120 ohm. Okay. And it can maximum withstand a current of 2.5 milliampere. It gives a full scale deflection with this current. Okay, it cannot allow more current to pass through. Okay. Now, how will you convert the galvanometer into ammeter? Ranges 7.5 ampere. So what will happen if you want to make an ammeter? Then 7.5. This is a very. So this is Alexa, stop. So this 7.5 ampere is how much? This 7.5 ampere is a huge current, so we have to split this 7.5 ampere current into two. One will go through this, and the remaining means 7.5 minus 2.5 into 10 to the power minus 3 milliampere. Na? So this current to be passed through this, for this we need a low resistance called shunt, correct? So we have to apply a shunt here. So this is how we can protect this galvanometer by connecting a resistance which is of low value, then only this will pass through in parallel with the galvanometer. So, okay, determine the net resistance of the ammeter. So let us do this calculation. Okay, so now when this shunt is connected in parallel with the galvanometer, then these two are parallel. So what is the potential difference across the galvanometer? What is current? 2.5 milliampere is the current, into galvanometer resistance is 120 ohm equal to, and this is in parallel with the shunt. So what is the potential difference shunt? Current into resistance. What is the current? 7.5 minus 2.5 you are passing through the galvanometer, so this much current is reduced, correct? Reduced 10 to the power minus 3 into the shunt resistance. So by this way you can find out the shunt resistance, correct? Okay. And the net resistance of the ammeter we can find by connecting a shunt of this with the given. So we get ammeter range 0.75 ampere. Now these two resistors, 120 is the galvanometer resistance, and shunt resistance is we have calculated as 0.04. This is a very low resistance, correct? So what is the effective resistance of this combination? Parallel 120 into 0.04 by 120 plus 0.04. Okay. So an ammeter is put in the circuit, it is slightly less than the actual current. Ammeter has a small resistance. When it is connected in the circuit, it decreases the current by a small amount. The resistivity, define the term resistivity, write SI unit, derive the expression for resistivity of a conductor in terms of number density of free electrons and relaxation time. Okay, this we have already solved. This question, state principle of potentiometer, draw the circuit. Okay, primary cell, write the formula used. So this is a repeat question. Comparison of cell is there in the potentiometer. So next class we will discuss about magnetic effects of current and magnetism. Okay, so here we'll discuss about moving charges and magnetism, Oersted experiment, Biot-Savart law, application of Biot-Savart law, and current due to a coil, circular coil at its center, at its axis at a distance say x. Because of this current, what will be the magnetic field here at this point at a distance x from its center. So then we'll discuss Ampere's law, the magnetic field due to infinitely long charged wire. Okay, then solenoids, then force on the moving charge, uniform magnetic field. Okay, force on a current carrying conductor in a uniform magnetic field, force between parallel current carrying conductors, definition of Ampere, torque experienced by a current loop in uniform magnetic field, like in moving coil galvanometer. So better current sensitivity and conversion of ammeter to voltmeter. So better if you go through the theory of it that is available, okay, in this channel, that how the moving coil galvanometer works, then it will be easier for us to solve the numericals. And magnetism ammeter concept, current loop, magnetic dipole moment, okay, magnetic field intensity, dipole bar. Okay, so torque experienced by magnetic bar magnet, uniform magnetic field. Okay, different types, different properties of materials, paramagnetic, diamagnetic and ferromagnetic substances, electromagnets and factors affecting the strengths and permanent magnets. Okay, so we'll resume our discussion in next class, correct? Okay, thank you.